Hello, Earth Science classes. Welcome to your lecture on the electromagnetic spectrum. First of all, I apologize for being absent last couple days. I really hate missing school, especially towards the beginning when we're starting new things. So I wanted to move forward with content today. I know yesterday you guys watched that video on the sun. I heard the sub passed out the answer key to the questions. So you guys better have all those questions right. Anyways, today we're going to start on the electromagnetic spectrum. I'm just going to do a brief lecture for you and then describe what you should be doing the rest of class, your assignments, things like that. But I promise I will be back on Wednesday for intervention. So you guys will actually have intervention for period 2 on Wednesday. But if there's anything you missed or any have questions, you're welcome to come in on Wednesday. If not, I will see you in class. Okay, so this week we're moving forward. Remember I told you guys that we're starting with the universe. I'm going to have you guys take notes today. Again, they're quick. You should have a worksheet that looks like this. Here, let me move forward. So it says the electromagnetic spectrum on top. It is set up in Cornell style. I again made it so that you don't have to write too much and just put in the missing here. In the margins, there's a couple things when I flip lectures and talk like this. You're welcome to add some diagrams that are on here. You're also welcome to add any extra information. So there's some things I'm going to have you write down. There's other things I'm just going to say that you can add to your margins. Remember, our margins are meant to be interactions, something further than what's going on in this content here. Okay, so the electromagnetic spectrum, it has their notes. We're, again, talking in context. You may have heard about the electromagnetic spectrum before, especially if you've taken physics. You probably had some introduction to it in your middle school science or even in biology. So why we talk about an earth science is because we use light, the electromagnetic spectrum, as evidence of our universe. Because we are not able to travel far distances, but light is able to. Light is able to travel from the other stars to us, and we can record it. Light is able to travel from us to other stars, and we can record that and see how it behaves. So we use light as kind of this way to go out into the universe and collect data, and even though we are not able to, right? So we have different instruments. As definitely as technology has progressed, those instruments have changed. But that's what we'll be looking at today. So what you need to know about the EM spectrum in context to earth science. Okay, so a little bit of review maybe if you've taken physics. If not, just make sure you pay attention to the astronomy connotations. So let's start with fusion. Fusion, what you need to know for astronomy. So to fuse is to put two things together. Fission is when you pull two things apart. So you may have learned about hydrogen fusion in bombs, right? So in World War II or as nuclear warfare. What you need to know about fusion in astronomy is that it fuels all cells. It fuels all stars. I just did a biology lecture. So it fuels all stars, and stars are what we're going to look at in our universe that tell the story of the past and how our universe was created. Our sun is a star. It's actually a main sequence star that fuses together hydrogen and hydrogen. These two coming together make the element helium. Right, so the hydrogen is kind of the ingredients. The helium is what's created. But when that process occurs, so when I'm putting two things together that don't want to be together by nature, a lot of energy is released. Right, so that's what you need to know about stars. Hydrogen fuse together with helium and lots of energy. Okay, now that energy comes in the form of a couple different ways, but light is emitted from our sun. Light is an energy. There's other things like heat, infrared, and all these other waves that we're not able to see. Right, so we'll talk about the EM spectrum and that the only thing visible to us is our visible light. Hold on, my son's going to come into the room here. Anyway, fusion is what fuels our stars, right? It's the stuff that comes together and reacts. So all of that energy is released, and what we see when that energy released is the waves of the electromagnetic spectrum. So that energy is released in a wave, and we'll talk about waves a little bit in this class, but I want you guys to see that, like the combination of electromagnetic, right? So there's electrical properties of these waves, there's magnetic properties of these waves, but those waves can be classified in 7 different wave types. Okay, so I want you guys to list out the waves there instead of have it in the paragraph. So the 7 different types of waves from the electromagnetic spectrum. So we're going to start all the way with the highest energy wave, and that's going to be gamma. All right, so you've got your gamma waves right here. And I want you guys to list these things out, but I'm also going to draw it at the end of class. All right, so my gamma waves start here, right? And as I move down my spectrum this way, right? So I'm going this way. The next high energy wave we have are X-rays. And then we have ultraviolet, and we usually call ultraviolet waves UV waves. They're the ones that give us sunburns. They're the ones that come to Earth quite often. The very small part of the electromagnetic spectrum right here is our visible. This is light we can see. It's very hard to imagine other types of light because our experience, we've talked about a lot about how our experience shapes our understanding of the world. Our experience tells us that we can see light. So I want you guys to kind of get rid of that notion that we have to be able to see it in order for it to be light, because all of these are types of light waves. The type that our eyes are attuned to are called visible waves. It's a good word for it, right? It's the stuff we can see, okay? But all these other types are still light. So as I move down here with lower energy, right before it I get infrared, right? And infrared is going to be like my heat source. And then I have microwaves and radio. But what you're going to see is as you move down this way, right? So going from gamma to radio, I get a decrease in energy. So those waves, even though they're all considered electromagnetic waves, are decreasing in energy as they change from one to the other, okay? As I go the opposite, if I go from radio to gamma, they actually increase in energy, okay? And so we say that the types of waves can change. Waves can slow down. That's most often what they do. They enter our atmosphere as visible and then they stay as infrared. You may have had this experience in a parked car. We'll talk about that a little bit more. But I get a decrease in energy as I move down, and I get a change in wavelength. So you can actually see that from one wave to another, the actual length of the wave changes. Okay, and so those are important relationships you need to know, especially for our evidence of the universe. So what you need to know with energy and wavelength, and like I just verbalized this, you can go ahead and fill in the blanks now. As I move from radio to gamma, right? So as I move from those long wavelengths to the short wavelengths, I get a wavelength decrease, right? So the actual distance in between the waves changes, right? So if here is my wave here, I'll draw it for you. My wavelength in physics, or when we talk about this in psychology with sound, is I'm saying the distance from one peak to one peak. Okay, so this is a peak, this is a peak. That's a wavelength. As I go from radio to gamma, my wavelength decreases, so they get closer and closer and closer and closer. And as those wavelengths decrease, my energy increases. Okay, so we have an inverse. My wavelength is decreasing, my energy is increasing. So we call that an inverse relationship. One's going up, one's going down. Okay, now the higher the energy, the more harmful those waves are. The shorter the wavelength, the more energy, right? So as you could go on from visible to X-rays and UV and gamma, those are really harmful types of EM waves, and we'll talk about those being released from the sun and how our Earth actually protects us for it. Most of our astronomy unit, we kind of focus on how the universe around us, what makes Earth so different, why we are able to have life on our planet because of the very special properties of Earth, what protects us from these EM waves. Okay, so here's your EM spectrum again. I'll get rid of this right here. But you just guys need to know that that is looking at the ones that are harmful to life and the ones that are not harmful to life. Okay, so the ones right here, so anything from visible, so visible is the one that's to our eyes that we're attuned to. Anything that it has less energy than that is not harmful to life in small amounts. Right? So of course, people always say, well, if you go into a microwave, you'll definitely get hurt. We're not talking about putting someone into a microwave. We're just saying the microwaves that are emitted from the sun that exist in our everyday life are not harmful to us as humans or life in general. Anything on this side with increased energy is harmful to life, meaning ultraviolet's able to, the wavelengths are so short, they're able to penetrate our skin, go into our DNA, cause skin cancer, cause our sun to burn, things like that. X-ray waves are so small that they're actually to go all the way through our skin and they reflect off our bones. but they're able to penetrate all the way through those other soft tissues, right? And gamma rays are actually used for things like cancer treatments. They're very harmful in large amounts. Think about anytime you've had an x-ray, you have to wear protective gear except over the area that's going to be photographed with those x-rays, and the guy hides behind the corner because the x-ray technician doesn't want to get hurt, right? So all of these, kind of backing up again, all of these are released from our sun. Our Earth has a very unique core. It's got an iron core, and it actually creates a magnetic field that protects us from these really harmful waves. And then other components of our atmosphere that we'll learn about are also protecting us from these waves, okay? But how this relates to astronomy, why are we talking about it at the very first lecture of the year, is that it actually gives us all of the evidence we need to look at the changing universe. And we're talking about something called the Doppler effect and the red shift, okay? And so what you need to know about wavelengths, as they become longer, they lose energy and they become other waves, right? So as they become longer, remember, the energy decreases and they become other waves. So I told you I would talk about this example, right? So you've been on a cold day, but your car is sitting in the sun. You have open up the door and it's really, really hot in your car, right? Even though it's not that warm outside. Or even worse, when it's 100 degrees outside and your car's been sitting all day, it's like 130 degrees in your car. Because visible light, when it goes through the windows, you can see it right here, it's able to penetrate the glass, but when it does that, it loses energy. It slows down. It becomes heat waves and no longer visible waves. And so that heat is too long now and gets trapped. This is called the greenhouse effect. It is used in greenhouses to grow plants, but it's also the same exact effect that happens in your car or any place where light is able to come in and it loses energy and slows down and becomes another type of wave. What we see about waves that are moving away from us is we also get a change in wavelength. Okay, so as objects move farther away from each other, the light actually shifts to a longer wavelength as well. And it changes from, it's called a red shift. It shifts towards a red. When something's coming towards us, the wavelengths get closer together. All right, now think about that in context of our universe. If our universe is expanding, if we're all flying through the universe, we are able to look at wavelengths coming from different stars. And it tells us a lot of information about those objects, how they're moving, how they've moved in the past, and how we relate to those objects. Okay, so a lot of the evidence we'll talk about from this point forward is talking about changing wavelengths. So you need a little bit of background on the electromagnetic spectrum. And that's the end of the electromagnetic spectrum lecture today. We'll talk a little bit more again, like I said, in the evidence of the Big Bang about it. But here's what I need you to do today. So once you finish your EM notes, you have all those blanks filled in. Make sure that you didn't miss anything. We'll be using them again. I want you to go ahead and flip it over. And on the back, you have your directions on what you need to do in the book. Okay, so the books are located above Station 3. Third period, if you wouldn't mind getting out the books, you can keep them on the desk. And then fourth period, if you would please put them away at the end of class, okay? But on the back, you have this worksheet right here. It says the EM spectrum. First thing I need you to do is on page reading upside down, 613. I want you to actually color, diagram, and label that electromagnetic spectrum. You need a colored version in your notes, all right? There are colored pencils on Station 2. I put those out for you guys again. Make sure you put them back, clean up after yourselves, check the floors before you go, okay? On the bottom of that page, there's just 4 questions I want you to answer from the book. You do need to read a little bit in between. Talks a little bit about the red shift, the Doppler effect, some things that you might be familiar with. And the last thing I need to do before you go, if you don't finish, I would expect you to come back for intervention on Wednesday. So I'll text out third period as a reminder to come back. But the last thing I have for you is a telescope article. So looking at technology and what we do with those electromagnetic waves, there's an article that says Telescope Trio will look back at universe birth. It's looking at 3 different types of telescopes. So if you flip it over, it talks about the Hubble, the Planck, and the Herschel. And I want you guys to read through the article, and then there's some organizer you need to fill out. You're looking at what country is in charge. It might be in multiple countries. There's like the European Union. You can just put that if you can't find a specific country. How does it see? So what type of telescope does it use, and the wavelength? And then what is it studying? Why are we spending all this money sending these telescopes out into space? So on this side here, I would like you guys to highlight the answers that you find, and then you're going to write the answers on this side. Okay. Again, I promise I will see you on Wednesday. If you did not finish your magazine cover, make sure that is definitely finished. I will collect your syllabus tomorrow, make sure that is signed, and make sure you have a notebook ready to go for tomorrow as well. All right, if you have any questions, just ask the sub, or you can email me. And like I said, I will be there Wednesday for second period intervention if you need anything. All right, hope you guys have a great day, and I will see you soon. Bye.